All right. Well, with 6 electron groups in total, with some of them being lone pairs, first of all, the electron geometry in every case is going to be octahedral. So remember, the octahedral is like this. It's like 2 square pyramids stuck together base to base. So this will be the arrangement of electrons, and then we just have to decide what it looks like when you start ignoring positions because they're lone pairs. So in every case, the electron geometry will be octahedral. The first possibility would be, what if you have 6 electron groups total and 5 of them are bonding and there's 1 lone pair? This would be, according to the table, this would be 651. So those would be the first 3 numbers in the table over on the left-hand side. And you follow it across and it'll tell you basically most of the things you want to know about that type of molecule. One example of this type of molecule would be BRF5. For the Lewis structure, BRF5 looks something like this. One of them is going to be a lone pair, and the rest of the positions, will be fluorines, and I've only drawn 4. Okay. Okay, I originally left out 1 fluorine, so this looks kind of weird, but it's an acceptable Lewis structure because it shows you what is bonded to what and how it's bonded. And that's what Lewis structures are for. So it's ugly, but it works. For the VSEPR theory, what it really looks like is what matters. And so for VSEPR, we would have to, first of all, decide where does that first lone pair go. Well, remember, all positions in an octahedron are equivalent. So it doesn't matter where that first electron or that first lone pair goes. It's easier to visualize it in certain places, though. So for this one, I'm going to count the one on the bottom as being the lone pair. So now the hole there, that's the lone pair. And the molecular geometry would be what we have left. And notice that if I had, say, taken this one off instead, we get the same result because it might look different, but what about now? Yeah, it's the same no matter which one you take off. So we end up with this. This is what's known as a square pyramid. And we can think of that as like this. You could draw it like this if you want to emphasize the electron geometry, or something like that if you want to emphasize the molecular geometry, with the xenon or the bromine being at the center. Okay, and that's essentially what we've got here. And see, it really is flat, and if you fill in the sides, you get a 4-sided pyramid. So we have the electron geometry is octahedral because there are 6 groups of electrons. And the molecular geometry is square pyramid. Okay, further possibilities. What if you have six electron groups total, and 4 of them are bonding groups? And 2 are lone pairs. Or in other words, 6, 4, 2, according to the table. Actually, when a second lone pair enters, the position does matter. Because of the extra repulsion that lone pairs have, the second lone pair is going to want to be directly across 180 degrees away from the first one. So the second one is going to go directly across from the first one. So it's not going to be one of these, it's going to be that one. So now we got two lone pairs. And look what you got. It's a flat square. So the Lewis structure of this example, actually F4 is a good example of this type of molecule. The Lewis structure would be something like that. With the two lone pairs. Remember, for the Lewis structure, you don't have to draw the lone pairs opposite each other because, again, the Lewis structure is just meant to show you what is bonded to what else and how. But for the VSEPR structure, things like that do matter. And the way we would draw this would be basically an octahedron. And it doesn't really matter which side, which bonds you draw as the lone pairs, as long as the lone pairs are directly across from each other. So that's one possibility if you want to emphasize the electron geometry, or if you want to emphasize the molecular geometry, you could draw it like that. Basically looking at it kind of like this. And so that's your shape. The, oh, I didn't actually name these, did I? Oops. The electron geometry, of course, is octahedral. The molecular geometry is square planar. The book doesn't really go beyond this level, but of course it's conceivable that you could have a third lone pair of electrons in something like this. And let's see if no, it doesn't even list it in the table. Basically, that would be 6 electron groups altogether with 3 lone pairs and 3 bonding groups, so 6, 3, 3. And, well, for the next lone pair, it would have to go to one of these guys. And basically, you would end up, once again, with a T-shaped molecule. And if you ended up with a 4th lone pair, or 6, 2, 4, then you would end up, once again, with a bent molecule, like that. Those are pretty rare, and like I said, it's not even covered in the book, so I'm not really going to spend much time on that. The next thing would be a procedure in the book for how to determine the molecular geometries. So this is under section 10.4. Under predicting molecular geometries. And there are certain steps that you need to use if you want to predict the molecular geometry of a molecule. And as long as you use those steps in the correct order, then you should be okay, at least with the kinds of molecules that we're likely to encounter in this class. So there are certain steps, like I said. The first step is draw the Lewis structure. And then you go on to the next step. And yes, I'll always love the way that they throw in like step one, do the Lewis structure, as if that's just like a snap. Do the Lewis structure, and we'll work an example or two. And then two, you have to determine the total number of electron groups on the central atom. And that will tell you the electron geometry. And then you have to determine how many of them are bonding groups and how many lone pairs. Okay, so bonding groups versus lone pairs. And then four, see the table on page 408, I believe it is. Yep, 408. And essentially what you're doing is you're positioning all of the electron groups as far apart as possible. In 3 dimensions. And then you can name the electron geometry. If you haven't already, you could have named it up here in step 2. You would have had enough information. And then name the molecular geometry. And then the molecular geometry, of course, is based on the position of the bonding groups only. And the bonding groups correspond to the positions of the atoms. So for an example of that, we have ClNO. It's useful to know in this case that the nitrogen atom is the central atom, and that's why it's written the way it is. And when we do the Lewis structure, well, first of all, let's actually do that. The first step to a Lewis structure is place the atoms in the correct relative positions, or in other words, the skeletal structure. So we know that nitrogen is in the center. It wouldn't matter if we switched the chlorine and the oxygen, as long as the nitrogen's in the center. That's the important thing. Then you total up the valence electrons. Chlorine has 7, nitrogen has 5, oxygen has 6, and that adds up to 18 valence electrons. All right, start by connecting the nitrogen with the outer atoms with single bonds for now. That uses up 4 electrons. Then we complete octets around the outer atoms. So we've used 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. We've got 2 left over because we know the total is supposed to be 18. So we put those on the central atom as a lone pair. Now, check for octets. If you check for octets, chlorine has an octet. Well, we made sure in a previous step that it has an octet. So yes, it does have an octet, as does the oxygen, but the nitrogen doesn't. Nitrogen's only got 2, 4, 6 electrons around it. So the only way that you can get nitrogen to have an octet would be to force one of the outer atoms to share a pair of electrons with it. Of the 2, oxygen or chlorine, the oxygen is much more likely to form double bonds than chlorine is. And so that ends up being the 1. So you would make oxygen share its lone pair of electrons, which means it's not there anymore. And this would end up being your Lewis structure. The central atom has 3 electron groups on it. In total. Two of them are bonding groups. The single bond counts as 1 group. The double bond counts as 1 group. So that's 2 groups that are involved in bonding. And there's 1 lone pair. So this is 3, 2, 1 in the terms that our table uses. And we can just look that up on page 408. So 3, 2, 1 corresponds to corresponds to a trigonal planar electron geometry. And a bent molecular geometry. For the VSEPR shapes, you would have something like this. Like I said, you don't actually have to draw the lone pairs on the outer atoms for a VSEPR structure, but I did anyway in this case. So this would be emphasizing the electron geometry, trigonal planar, as you can see. Or if you want to emphasize the molecular geometry, you can draw it like this. That's a CL there. And that emphasizes that the molecular geometry is bent. And for larger molecules, we aren't really going to do any molecules much larger than the ones we've seen so far, but you can actually scale this method up to larger molecules. Basically, you just predict the shape around individual atoms and compile the information into an overall model. So something that's a little bit bigger, but not a lot bigger than what we've done so far is ethanol. Ethanol has a Lewis structure that would look like this. And you can actually just look at the individual cases here. The interior atoms, we don't care about the exterior terminal atoms, so we don't care about the hydrogens here, but looking at the interior atoms, we've got the carbon there. Carbon has okay, so the carbon has 4 electron groups total on it. All 4 of them are bonding groups. None of them are lone pairs. And so the electron and molecular geometry for that carbon would be tetrahedral. And the same for that carbon, actually. The oxygen has 4 electron groups total also, 1, 2, 3, 4, but 2 of them are bonding and 2 are lone pairs. And so what that means is the electron geometry is tetrahedral, but the molecular geometry would be bent around the oxygen. And then taking these facts into account, you can actually build a larger model, or you could think up a larger model in your mind and come up with what it might look like. Okay, so here's a carbon, and we know that the carbons have to be tetrahedral, so we might have a hydrogen coming out like this, and one going back in like this, and here we'd have one maybe coming out like this, and one going back in like that, and one in the plane. So it'd end up looking maybe something like that. And if you give me a moment, I will build a model and we can